in this module, we are going to discuss the multiplication property of continuous time Fourier transform. In the previous module, we saw the convolution property, which states that convolution in time domain corresponds to multiplication in the frequency domain. Now, multiplication property is a dual of the convolution property, that is, multiplication in time domain corresponds to convolution in the frequency domain. So more specifically, if we have a time domain signal RT, which is the product of two signals ST and PT, then the Fourier transform of RT is Rj omega, where Rj omega is 1 over 2 pi Sj omega convolved with Pj omega, or 1 over 2 pi minus infinity to infinity Sj theta Pj omega minus theta d theta. So multiplication of signals in time domain corresponds to the convolution of their Fourier transforms, and there is a factor of 1 over 2 pi in the output as well. We can derive this property using the Fourier transform relations, and the proof will follow somewhat similar procedure that we saw in the derivation of the convolution property. And I'm not going to prove this property. Sometimes we refer to this property as modulation property. So another name for this property is modulation property. Because when we multiply two signals in time domain, this process is often referred to as the amplitude modulation process. And this property has several useful applications, mostly in communication systems. And in this module, we will discuss the modulation and demodulation applications of this property. So here we have a signal Sj omega. The spectrum is located around lower frequencies. The spectrum is located centered at 0 frequency, and we are assuming that omega 1 is not very high. Now we want to shift this spectrum to some other frequency band. The primary purpose of shifting this spectrum is to produce a signal that is more suited to the characteristics of the transmission channel. And this shifting of the signal from one frequency region to another frequency region is called modulation, because this can be done with the help of the multiplication property that we have just shown at the top. So and modulation basically is the fundamental operation that we do in the communication systems, because modulation permits us to place a signal wherever we want in the frequency band. And because of the modulation, multiple radio and TV stations, they can simultaneously broadcast their transmissions in a given area, because each station has a different assigned carrier frequency, and they produce and transmit their signals in that frequency range. And on the receiver side, we can separate out the signals coming from different stations with the help of frequency selective filtering that we saw in the previous module. And only because of the modulation, multiple TV and radio stations can operate in a given area. Okay. So in this example, our objective is to translate the spectrum of Sj omega to another frequency omega naught. And omega naught is greater than omega 1 so that there is no overlap. The shapes of the given signal and the translated spectrum, they are the same. It means the information is preserved. Like we saw in the time shifting, when we shift the signal in time domain, the signal remains the same, but it's just a shifted version of that signal. Similarly, when we shift the signal in the frequency domain, the information in the signal, it stays the same. Only that now it is located in a different frequency band. So here we can apply the multiplication property. Let's say ST is this time domain signal. To achieve this modulation, what we can do, we can multiply ST with another signal PT. And we have already seen that if PT is a complex exponential ej omega naught t, its Fourier transform is 2 pi delta omega minus omega naught. If we use the multiplication property, R j omega is 1 over 2 pi S j omega convolved with 2 pi delta omega minus omega naught. So 1 over 2 pi will get cancelled with 2 pi and we will get Sj omega minus omega naught. Because when we convolve any signal with an impulse, we get back the same signal. And if we convolve a signal with a shifted impulse, we get a shifted version of that signal. Now, in this example, we want to do the modulation, but instead of using a complex exponential, here we use a cosine carrier, cos omega naught t. That is, now we want to modulate ST by multiplying it with cos omega naught t. And we know that cos omega naught t, its Fourier transform comprises of two impulses. One impulse is located at omega naught and another impulse is located at minus omega naught. And this is how the transform of cos omega naught t looks like. We have one impulse at omega naught and we have another impulse at minus omega naught. And the areas of both the impulses are pi. So this is our Pj omega. And applying the multiplication property, Rj omega will be 1 over 2 pi S j omega convolved with pi delta omega minus omega naught plus pi delta omega plus omega naught. So we get half Sj omega minus omega naught plus half Sj omega plus omega naught. So what have we done here? When we multiply a signal in time domain with cos omega naught t, we translate the spectrum of the signal and we get two copies of the spectrum. One copy is located at frequency omega naught while another copy is located at minus omega naught. And there is this scaling of 1/2 as well. So this is how Rj omega will look like when we multiply St in time domain with a cosine carrier. And there is a scaling of 1/2 as well. Okay, in the next example, we consider demodulation. Demodulation is the process of bringing back the signal to the original frequencies. Now this is R j omega, and from this R j omega we want to recover our original signal. That is, we want Sj omega back. So we want it back from this one. So once again, it involves shifting the spectrum to lower frequencies, because Sj omega was located at lower frequencies. And we multiply RT with cos omega naught t. So to demodulate the signal, we multiply in time domain the inverse Fourier transform of this signal with cos omega naught t, and applying the multiplication property, we would get g j omega equals 1/2 R j omega convolved with the Fourier transform of cos omega naught t, which are two impulses, plus pi times delta omega plus omega naught. So half R j omega minus omega naught plus 1/2 R j omega plus omega naught, where R j omega is 1/2 S j omega minus omega naught plus 1/2 S j omega plus omega naught. So have we recovered Sj omega by multiplying RT once again with cos omega naught? Let's see. So what is Rj omega minus omega naught? This is Rj omega. If we shift it by omega naught, we can write the right hand side as Sj omega minus omega naught minus omega naught plus 1/2 Sj omega plus omega naught and minus omega naught. And R j omega plus omega naught is 1/2 S j omega minus omega naught plus omega naught plus 1/2 S j omega plus omega naught plus omega naught. Now we can see that here in this term, Sj omega plus omega naught and minus omega naught, it will give us half Sj omega. And we put both these values in equation 1. So Gj omega is 1 by 4 Sj omega minus 2 omega naught. These two will add up, and there is 1/2 scale factor already in 1. So we get 1/2 Sj omega plus 1 by 4 Sj omega plus 2 omega naught. So here is our desired term. When we multiply RT once again with cos omega naught t, we indeed get Sj omega, which is centered at 0. So this is centered at omega equal to 0. While there are additional copies of the signal of the spectrum, and this one is centered at 2 omega naught, and this copy of the spectrum, this is centered at minus 2 omega naught, and there is scaling as well. And this is how the signal, the output Gj omega looks like. This is our Gj omega. This copy is scaled by 1/2, and these two by 1/4. Now, having come this far, we can recover the original signal with the help of frequency selective filtering. If we design a filter, let me write, we can recover Sj omega using frequency selective filtering. If we design a filter with frequency response Hj omega equal to 2 in this frequency band and 0 outside these frequencies, then Gj omega multiplied by Hj omega will give us Sj omega, and this is convolution property. In the demodulation process, we use the multiplication property as well as the convolution property to recover the signal Sj omega. And one last thing, we can think of the same operation in another way. Gt is RT times cos omega naught t, where RT itself is St times cos omega naught t. So Gt is RT cos square omega naught t. And if we apply a trigonometric identity on cos square omega naught t, we will get RT half plus 1/2 cos 2 omega naught t, which is 1/2. Sorry, this is St multiplied by cos square omega naught t, and this is st because here we are replacing rt with st times cos omega naught t. We get 1/2 st plus 1 by 4 st times cos 2 omega naught t. And this thing will again lead us to the same frequency spectrum. Here we can see 1/2 s j omega term, and from this second term, this is the multiplication of st with cos 2 omega naught t, and cos 2 omega naught t comprises of two impulses located at 2 omega naught and minus 2 omega naught that will produce these copies, this one and this one.